Okay, are you all ready? I'm going to start the class now. Okay, today lectures I will continue with the CMOS inverter. Okay, this is also the DC characteristic of one of the inverter. Okay, today's I will finish this topic about CMOS inverter. Okay, I will cover the calculation again on the critical voltages, the calculations of the voltage. Okay, in CMOS inverter. Okay, this one I know most of you are familiar. What is it? Okay, and in this topic, okay, today I will recap. Okay, I will recap some of the theory here. Okay, then after that I will go to the next topic. Okay, uh, CMOS inverter. Okay, this is CMOS inverter, figure 5.16a. The following equations describing the current and voltage relations of NMOS and PMOS transistors. Okay, previously what we see in the inverter, it is with drain current and then the load current. Okay, but for this inverter, it is with only drain current. Okay, the drain current of the PMOS and the NMOS. Okay, and then all the voltage here are labeled as VGS, VDS. Okay, so VGS is the gate to the source voltage, and then VDS is the drain to source voltage. Okay, and what is the relationship? I will mention here. Okay, here given the equations, the drain currents of PMOS is equivalent to the drain current of NMOS. Okay, when there is a current flow from the PMOS, then the currents flow from the drain terminals to the drain terminals of the NMOS. They are equal. Okay, and then for VGS, okay, VGS N. Okay, this is the VGS for the NMOS. Okay, VGS NMOS, we also can call it as V in. Okay, and then for the VGS N, VDS, VDSN, this is the drain source voltage. Okay, this is the output. Okay, if you refer to this figure, you can see the label already given here. Okay, V out equals to VDS, and then V in is equals to VGS. This is for the NMOS. Okay, and then for PMOS, okay, before that, okay, this is the additional um, equations that I want to show you. VGS N means it is VG, the gate at the voltage at the gate minus the voltage at the source. Okay, why it is also can call as V in, because VG is V in minus 0. Okay, VS here, because here at the source terminal, the voltage here is connected to the ground, so this is 0. So that's why it is equivalent to the input. okay, for VGSN. Okay, whereas for VDSN, VD is the output. Okay, the output voltage here at this point, this is the drain terminal. This is the voltage at the drain terminal. So VD, and Vs again is also 0, so it is V out. Okay, for VGSP, this is the VGS for the PMOS. Okay, the sign you see here, it is minus VDD, negative, this is sign, negative sign, sorry. This is negative sign, VDD minus V in. Okay, how to get this? Okay, again, we can define VGS as VG minus Vs. Okay, VG, we know it is V in minus VDD. Okay, VDD because Vs, the source terminal here is connected to the VDD. Okay, is connected to the VDD. So this is VDD. Okay, that's why this is the equations that is given. Okay, for VGS PMOS. Okay, from the definitions, from these definitions. Okay, and then the sign here, I think you know. Okay, we make an arrangement here. This is positive. Okay, but you see this is negative because VDD minus V in. Okay, for VDS as well, VDS of the PMOS, it is equals to negative VDD minus V out. Okay, to get this again, VDS is defined as VD minus VS. Okay, so VD here is V out minus VS. VS here is VDD. So that's why this is how we get the equation. Okay. Okay, for CMOS inverter, there are also three operating mode. Okay, the three operating mode, as you remember, it is cutoff, linear, and saturation. Okay, so there are different conditions at the output that will cause different operating mode of the transistor. Okay, so in case one, this is case one. Case one is when the input is 0. Okay, means the input is low. Okay, and then V out is high. Okay, then the threshold voltage is also given. There are two threshold voltage. One is for the NMOS and another one is for PMOS. Okay, NMOS, the threshold voltage is 1 volt in this case. Okay, and then for PMOS, the threshold voltage is minus 1 volt. Okay, you must remember that for threshold voltage, okay, both PMOS and NMOS, the threshold voltage will almost the same. Okay, except that PMOS, usually the voltage is in negative. Okay, is in negative sign. Okay, if there is a negative sign, means that threshold voltage of the PMOS will be smaller, okay, than the NMOS. Okay, why is that? Because the PMOS will start to operate at the low voltage level. Okay, so its a threshold voltage normally will be lower than the threshold voltage of the NMOS. Okay, so this is the difference. Okay, so uh, here there are a few of the calculations here is to show the VGS and VDS value, okay, for PMOS and NMOS, and then also to show them their operation mode. Okay, so for this one, if we want to calculate the VGSP, so we need to use back the formula here. This is negative VDD minus V in. Okay, so VDD here is already given. It is 5 volt. Okay, and minus V in, it is 0 volt. So VGSP, this is the output. Okay, is minus 5 volt. Okay, not output, sorry, this is input. Okay, this is at the gate. Okay, at the gate voltage, it is minus 5 volt. Okay, minus 5 volt, and then at minus 5 volt, the PMOS actually operate in linear region. Okay, and then the VDSP is a 0 volt. Okay, is Okay, if I label here means VDS, this is 5. Okay, the sign here is the balik. Okay, this is should be minus 5 volt, but the magnitude here is 5 volt. Okay, and then the VDSP is actually 0 volt. Okay, so and then for NMOS, the VGS is a 0. Okay, means the gate voltage is 0. It can be a logic 0. Okay, and then the NMOS is in cutoff. Okay, and the output of the NMOS is 5 volt. It is high. Okay, so this is how we should evaluate the CMOS inverter using VGS and VDS. Okay, this one later I will talk on the VTC. I will continue to the case 2. Okay, this is another conditions where the input voltage is increased to 3 volt. Okay, and then V out, okay, is reduced to 2.5 volt. Okay, initially the V out is 5 volt, now is 2.5 volt. Okay, and the threshold voltage again is the same. Okay, we also can determine the VGS and VDS. Okay, we can expect that when the input voltage is increased, then the NMOS maybe will start to operate. But before it operate in linear, NMOS will be in saturation mode first. Okay, and then for PMOS will start to turn off, but before turn off, it will goes to saturation mode first. Okay, this means that they are partially off or partially on. Okay, so for this one, PMOS, all the calculations of VGS and VDS is assured here. Okay, you doesn't really need to remember what is what is the value, okay, for each of the terminal here. This is just to show you the conditions of the VGS and VDS when the input is 3 volt and the V out is 2.5 volt. Okay, so I goes to the next case. Okay, case 3 where the input is increased to 5 volt. Okay, this is high input voltage. Okay, V out is reduced to 0 volt. Okay, and then we also can expect that PMOS is in cutoff and MOS is in linear region. Okay, for PMOS, when it is in cutoff, the VGS of the PMOS is 0 volt. Okay, it is above the threshold voltage, means the minus 1 volt. Okay, it is larger. Okay, it is larger. And then for the VDS, its value is minus 5 volt. Okay, so in this case where the input voltage is high, okay, to the PMOS, the PMOS will not operate. Okay, that's why it is in cutoff. Okay, for PMOS, it is inverse. Okay, it must operate when the input is high. Okay, so this is how we should understand. Okay, this all the cases here I show you. Hope that it can help you to revise back. Okay, all these operating modes. Okay, so these 3 cases we can apply it on this VTC. Okay, this is a typical CMOS inverter voltage transfer characteristic. Again, you see that there is a curve here. Okay, this is the curve of a VTC for CMOS inverter. Okay, since this is, VTC is not the ideal inverter. Okay, there is not there you see the curve here is not a sharp transition. There is a slope also. Okay, means that the transitions happens very slow. Okay, so you see here labeled as A, B, C, D, E, means that they are operating in different region. Okay, for A here, when the VDD is high, okay, and the input, this is the input voltage, this part, Okay, this part is input voltage, means the input voltage is low. So the PMOS linear and MOS cutoff. Okay, so this is how you should understand. Okay, since there are two transistors here, so two different transistors, they operate in different mode. Okay, and then at this point, uh, point B, okay, the input voltage increase above the threshold voltage. Okay, and you see that NMOS saturated, PMOS is still linear. Okay, means the PMOS is still operate in linear mode. Okay, NMOS still turn off, but it start to operate. Okay, and then when the input increase, output will decrease. Okay, at this point C, okay, both NMOS and PMOS are saturated. Okay, they are saturated. And we expect that NMOS will turn on and PMOS will turn off if after the input voltage is further increased. Okay, and then you see the point D here. Point D is at which the input voltage is VIH. Okay, and the NMOS now start to operate in linear and PMOS in saturated. Okay, and then E, NMOS is linear and PMOS is cut off. Okay, so this is how we should understand the VTC. Okay, it shows all the operating modes for all the transistors. Okay, and then this one is a table that summarizes all the input conditions and with the output and the operating mode for the NMOS and PMOS. So this one I will leave it to you. Okay, it will help you when you study back. Okay, so this one I already explained just now with the use of the VTC. Okay, now it's about the calculations. The calculations here is the calculations of VIL. Okay, again, you see there is equations, some of the equations here. Don't worry, you no need to memorize. Okay, you also no need to understand. Okay, if you want to understand also can. Okay, you take your time to understand how is the derivations done. Okay, but for this one, I don't need you to understand all together. Okay, I know that maybe you will take more time to understand all on how to derive the formula. Okay, but what I want you to know is if to calculate the VIL of the CMOS inverter, then this is the formula. Okay, there is a V out and then the threshold voltage for the PMOS and the threshold voltage of the NMOS and also the KR. Okay, again, this KR um, is the ratio. Okay, the NMOS to the PMOS ratio. Okay, okay. I don't know what this K mean. How they call this K, but I usually call this as just K. Okay, and K is defined as K prime W over L. Okay. Okay, so when I say K, so you should know. Okay, so I hope you know how to differentiate all the formula. Okay, several critical voltages formula explained to you. Okay, uh, each of the inverter has different structure, not different structure, they are similar structure but use different transistor. Okay, so the formula slightly varies based on what is the transistor used. Okay, for this one, since the PMOS and NMOS is used, so we should expect that there is a voltage level for PMOS and NMOS. Okay, so for this one, we should differentiate it based on the threshold voltage of PMOS and NMOS. Okay, if we want to calculate the input low voltage for the CMOS inverter. Okay, for calculations of VIH, okay, again also another formula. Okay, this one is also the equations that used to derive, okay, to get the formula. Okay, the derivation is similar to the ones that I explained to you before. Okay, if you study back, you will learn that all this derivation is based on the Kirchhoff-Current's law. Okay, so all the circuit, they have current, drain current and load current. Okay, so we use the current equations to differentiate it, okay, to differentiate it, and then we get the formula. Okay, this one also work the same. Okay, so the formula for VIH, this is the formula. Okay, VIH equals to VDD plus VDO P plus the KR multiplied with 2 V out plus the threshold voltage of the NMOS divide by 1 plus KR. Okay, when the VIH is not given, okay, in the questions, then you will have to use these formulas to calculate. Supplies voltage scaling. Okay, uh, this supplies voltage means the VDD. Okay, so the values of VDD we cannot simply choose. Okay, because we have to consider if we increase the supplies voltage, what is the effect? Okay, the effect can be good or can be good or bad. Okay, previously I mentioned before, if this VDD is high, then we can get a very high power consumption. Okay. Okay, so here already explained. Okay, the supplies voltage VDD has direct influence on overall power dissipations of any digital circuit. The exact shape of the VDC near the limit value is essentially determined by the sub-threshold conductions properties of the NMOS and PMOS transistor. Yet, it is clear that the circuit operates as an inverter over a large range of supplies voltage level. Okay, there is a graph shown here. Okay, it plot the output voltage versus the input voltage with different level of the supply voltage. Okay, so at this level, you see when the supply voltage is low, then the output voltage also will be low. Okay, input voltage will be will depends. Okay, will depends on what is the values that is input to the transistor. Okay, this graph, the curve getting higher with output voltage. Okay, when the VDD is increased, okay, to 5 volt. Okay, IV curve of CMOS inverter. Okay, this is about to plot the current. Okay, the currents versus the output voltage. In order to plot the DC transfer characteristic graphically, not input, this is current. Okay, this is current versus the voltage characteristic of NMOS and PMOS transistor are superimposed. Such graphical representations is called as a load line plot, okay, or load curve. Okay, this one also we can call as load curve. Okay, for a DC operating modes to be valid, the currents through the NMOS and PMOS devices must be equal. Graphically, this means that the DC point must be located at the intersections of corresponding load line. A numbers of those points for V in 0, 0 0.5, 1, 1.5, 2, and 2.5 are marked on the graph. Okay, so this is the load curve. Okay, I have shown you before for the resistive load inverter. Okay, this is for the CMOS inverter. Okay, the pattern is still the same. Okay, they behave the same. Okay, you see the graph here. it is plot with the drain current. Okay, this is drain current and versus V out. Okay, sometimes we use VDS. Some of the graph you will see that here it is VDS is not V out. Okay, and then you see there are different curve here. Okay, this curve, one is for PMOS and another is for NMOS. Okay, this one, as you see, this is for NMOS, the black line. Okay, the blue line is for the PMOS. Okay, since NMOS and PMOS, they work in inverse operation. Okay, so here you see the operations with the current and the output is also in opposite way. Okay, the different level of the line here indicate the amount of the current increase, okay, at different input voltage. Okay, so this one is the loop curve and this is another one is the VTC. Okay, this VTC is the one that I explained just now. Okay, it's the same one. Okay, so as a summary, the inverter is the nucleus of all digital design. Once its operations and properties are clearly understood, designing more intricate structures such as NAND gates, adders, multipliers, microprocessor is greatly simplified. The electrical behavior of this complex circuit can be almost completely derived by extrapolating the result obtained for inverter. The analysis of inverter can be extended to explain the behavior of more complex gates such as NAND gate, NOR gate, and exclusive OR gate, which in turn forms the building blocks for modules such as multipliers and processor. Okay, so this is the end of the topic about inverter. Okay, next they will be also going to have some more discussions on inverter, but it's on the dynamic characteristic of inverter. Okay, so these 2 weeks I mentioned about the static characteristic. Okay, so next topic I will mention on the dynamic characteristic. Okay, so any one of you have any question regarding this before I proceed to the new topic I need to know? Okay, today lecture class, I think we will end the class early today because some of the notes I haven't finished preparing. Okay, I have update some for today, but I haven't upload the lecture notes to you all. Okay, because I haven't finished update the notes, all the notes that I'm going to cover in the lecture class. Okay, I'm sorry about that, but I need to let you know. Today I will cover what I can cover. Okay, if I cover them early, then we can end the class early. Okay. Okay, so now I will start the next topic. Okay, dynamic logic circuit now. Okay, this topic is about dynamic CMOS circuit. Okay, so what is dynamic logic circuit? Later it will be explained. Okay, the okay, so between the static and dynamic circuit, okay, you can see the chart here. Okay, this chart shows the type of the circuit for digital circuit. Okay, so there is two branch. Okay, static circuit and dynamic circuit under digital circuit. Okay, static circuit, it will be about the classical CMOS, transmissions gate CMOS, and CVSL circuit. Okay, so previously I mentioned about CMOS. Okay, not CMOS. CMOS is on its static characteristic. Okay, but for transmissions gate CMOS and CVSL circuit, okay, it's not covered. Okay, I didn't cover both of these. Okay, so for dynamic circuit, there are domino logic circuit, okay, and LoRa logic circuit, and TSPC logic circuit. Okay, so I will cover the domino logic circuit and LoRa logic circuit. Okay, today, before I cover these two, I think I will not be able to cover these two because before the domino and LoRa logic circuit, I want to introduce you to another circuit called as pass transistor. Okay, and then also uh, another circuit that is used to reduce the threshold voltage. Okay, we call it as a voltage strapping. Okay, not so it's not voltage strapping. It's a voltage boot strapping. Okay, so that one I will cover. Okay, because I want you to know and learn. Okay, what is this circuit about? Okay, so introductions to dynamic logic circuit. In high density and high performance digital implementation, the reductions of circuit delay and silicon areas are the major objective. Dynamic logic circuit offer several significant advantages over static logic circuit. Their operations depends on temporary storage of charge in parasitic node capacitance instead of relying on steady-state circuit behavior. Consequently, the circuit require periodic clock signal in order to control charge refreshing. The abilities of temporarily storing a state, for example, a voltage level at the capacitive node, allow us to implement very simple sequential circuit with memory functions. Okay, so in this slide, it shows the difference between the dynamic logic circuit and the static logic circuit. Okay, the dynamic logic circuits, if you compare it and then you see the statements here, okay, you can know that dynamic logic circuit has the memory function. Okay, it has memory function. Okay, it has memory functions, and also this circuit, it can store the charge. Okay, at the output there is a capacitance. Sometimes we call it as output capacitance or parasitic capacitance. Okay, later the circuit will be explained how it is work. Okay, there is a one type of NMOS dynamic logic circuit. Okay, it is uh, in figure 9.1. Okay, consists of an NMOS pass transistor driving the gate of another NMOS transistor. Okay, if you refers to figure 9.1, okay, I try to write here. I'm not sure why. Okay, now okay already. Okay, this figure is a dynamic logic circuit. There are two NMOS. This is NMOS, and also this is NMOS. Okay, this NMOS has the output. Okay, the output is connected to a CX. CX called the parasitic capacitance. Okay, sometimes we call it output or load capacitance. Okay, the output, okay, the output drive another NMOS. Okay, when there is an capacitance connected at the output, and it can drive another NMOS. Plus the circuit is operate or is driven by the gate. This is called as dynamic logic circuit. Okay, this NMOS, okay, the first NMOS here, we call it as the pass transistor. Okay, this is the circuit that I want to introduce to you. We call it we call this as the dynamic logic circuit, okay, with a pass transistor in the circuit. Okay, this pass transistor is driven by the periodic clock signal. Okay, this is the clock signal. Okay, and act as an access switch to either charge up or charge down the parasitic capacitance C, depending on the input signal V in. Okay, there is an input voltage. This is the input voltage. When the input is high, okay, then here there will be current flow, and then the capacitance will be charged up. Okay, but when the input is low, then it will work in another way around. Okay, so later the operations of this circuit will be explained. Okay, there are two possible operations. Okay, the operation is based on the clock signal. Okay, the clock signal is either active or non-active. Okay, so first about the first operations is when the clock signal is active. Sometimes in short we can just write it in CK equals to 1. Okay, so when the clock signal is active, okay, there is two possibilities of input. Okay, one is logic 1 or logic 0. Okay, when the input voltage, okay, so I write here, this logic 1 indicate P in equals to logic 1. Okay, and this is the case when the V in is logic 0. Okay, for logic 1, the transistor, when it is on, okay, it will charge up the capacitance Cx to a logic high level. Okay, so means that when this V in is high, okay, the transistor will be on, and then here the Vx will also be high. Okay, output will be at high level voltage. Okay, Cx charge up. Okay, when the input is low, okay, when the input is low, then the output will remain high or low. Okay, you see here, okay, the pass transistor MP provide the only current path to the intermediate capacitive load node X. Okay, they are still current flow. Okay, except that the voltage level here, okay, we have to see, okay, some conditions maybe it still remain high, some conditions it remains low. Okay, and then the Cx here, initially it is being charged up. Okay, now when the transistor is turned off, okay, then it will charge down. Okay, this means it is discharged. Okay, this is about discharge. Okay, capacitance is discharged to a low level. Okay, if this is discharged to a low level, so means that Vx will also become low. Okay. Okay, and then another operation is when the clock signals become inactive. Okay, the pass transistor ceases to conduct and the charge stored in the parasitic capacitor Cx continues to determine the output level of the inverter. Okay, this is means that when the Ck is 0, okay, the transistor will stop operating. Okay, totally not operating, no matter the input is 1 or 0. Okay, so when the clock signal is 0 and the charge stored in the parasitic capacitance, okay, maybe some charge has already discharged, maybe some still have some charge still stored in the capacitor. Okay, so this the charge will depends uh, the charge will determines the output level, okay, of the inverter. Okay, so this is how we should understand the operations of this circuit. Okay, this is for you to understand further on logic 1 transfer, okay, and logic 0 transfer. Okay, for this one, logic 1 transfer, it is means that when the Vin is high, okay, and then the clock signal is 1. Okay, a logic 1 level is applied to the input terminal. Okay, Vin is equals to VOH and equals to VDD. Assume that the soft node voltage is equals to 0 initially. Okay, Vx is equals to 0 volt. The clock signal at the gate of the pass transistor goes from zeros to VDD at t equals to 0. Okay, at time, this is time, t is time. At time, when the circuit start to operate, okay, the clock gate will increase from 0 to VDD. Okay, the pass transistor MP start to conduct as soon as the clock signals become active. It will operate in saturations throughout these circles since VDS equals to VGS. Consequently, VDS is larger than the VGS minus the threshold voltage. The circuit to be analyzed for logic 1 transfer event can be simplified into an equivalent circuit, so it refers to this figure 9.2. Okay, there is a formula here, okay, but I'm not going to explain on this formula. Okay, I directly show the graph. Okay, this graph shows the operations of the pass transistor. Okay, uh, at the durations of time from 0 to VDD, and then the output Vx. Okay, and the output initially it is 0. Okay, when over a certain time interval, the voltage will increase to a level. Okay, this level is the Vmax. Okay, the Vx cannot exceed the Vmax, okay, the level should be at this Vmax or below. Okay, so the Vmax given here is equals to VDD minus the threshold voltage, VT. Okay, the voltage level, okay, you see here, there is a statement here which is quite important. The voltage rise from its initial values of 0 volt and approach a limit values for large T, but it cannot exceed its limit values of V equals to VDD minus VT. Okay, this V is the Vmax. Indicate this formula. Okay, the pass transistor will turn off when Vx equals to Vmax, since its gate to source voltage will be equals to its threshold voltage. Therefore, the voltage at node X can never attain the full power supplies voltage level of VDD during the logic 1 transfer. Okay, there is a problem here. You see that Vx is the output voltage. Okay, suppose output voltage should be equals to Vmax. Okay, to indicate that it is high. Okay, but that it cannot. Okay, it cannot be equal. Okay, or exceed Vmax. Okay, if this Vx is equal, the transistor will turn off. Okay, and the Vx is actually not equals to VDD. Okay, what I want to say is the maximum output, it should equals to VDD, but it is not equals to VDD if we want to consider the maximum value. Okay, why? Because the VDD here is minus. Okay, it is minus by the threshold voltage. Okay, it cannot attain the full power supplies voltage level of VDD. Okay, um, because of this. Okay, this one will be explained. Okay, maybe now you don't really understand what I mentioned here. Okay, you will have to go to read yourself later if you have time. Okay, and this one, for now, you just refer to the slides here. Okay, later you will know. Okay, what is mean by this. The node voltage V has an upper limits of Vx equals to VDD minus Vt. Okay, it has a significant implications for circuit design. Consider a chunk of cascaded pass transistor in figure 9.4 is with a logic 1 at the input node where Vin is equals to VDD. Initially, all internal node voltages V1 through V4 are 0. The first pass transistor M1 operate in saturations with VDS larger than VGS minus VTN. This is the threshold voltage of the NMOS. Okay, therefore, the voltage at node 1 cannot limit values Vmax equals to VDD minus VT. Okay, so this pass transistor M1 means this one. Okay, this is the transistor. Okay, work in saturation. Okay, and other transistor is also NMOS. They are identical. Okay, they also work in saturation. Okay, you see here at the output of each of the transistor, they are of the same voltage. Okay, the value maybe is not the same. Okay, let me see. Here given is VDD minus VT. Okay, the threshold here for each of the transistor, if different, then the node voltage here maybe will be different. Okay, but given here, assuming all the pass transistor are identical, it can that with VT equals to VT of the second NMOS and also the threshold voltage of the third NMOS. Okay, so if all the threshold voltage of all the NMOS is the same, so means that the node voltage here will also be the same. Okay, the node voltage is refers to V1, V2, and V3. Okay, so the anode voltage at the end of the pass transistor will become 1 transistor voltage lower than VDD, regardless of the numbers transistor in the chant. Okay, this is another dynamic logic circuit that consists of the pass transistor. Okay, there are another circuit. Okay, also a dynamic logic circuit. Okay, with just NMOS. Okay, this is with only 3 transistor NMOS. Okay, okay, and then you see the structure is slightly different. The output drive another transistor through the input. Okay, and then all the voltages here at the output node of each of the transistor. Okay, they are also defined as Vmax equals to VDD minus VT minus VT. This is the threshold voltage for 2 different transistor. Okay, at this node, okay, since it passed through 2 transistor, okay, so the threshold voltage of both transistor need to be minus. Okay, and then for this one, the VDD, okay, need to be minus with the threshold voltage of M1. Okay, the output of the first pass transistor M1 can reach the limit. Okay, Vmax equals to VDD minus VT. This voltage drives the gate of the second pass transistor, which also operate in the saturation region. Its gate to source voltage cannot exceed the threshold voltage of the second NMOS. Hence, the upper limit for the V2 is found as this. Okay, it can be seen that in this case, each stage causes a significant loss of voltage level. Okay, so that is the 3 dynamic logic circuit that I show. Okay, with numbers of the transistor, and then the structures also different. Okay, that is for the logic 1 transfer. Okay, means that when input is 1, and then how the circuit behave. Okay, and what is the values of the node voltage. Okay, so next, now I will mention about when the logic 0 is input to the transistor or input to the circuit. Okay, so at logic 0 transfer, okay, there is a logic 0 means that the logic 0 is applied to the input terminal. Vin equals to 0. Assume that the soft node voltage Vx is equals to logic 1 level initially. Okay, and Vx is equals to Vmax VDD minus the Vt. Okay, so here already show to you. Okay, except that here Vx here is Vmax, as not Vmax, this is VDD. Okay, I also can write here, this is V. Okay, just now I want to write Vmax, this is VDD equals to Vtn. Okay, this also means that it is equals to Vmax. The clock signal at the gate of the pass transistor goes from zeros to VDD. Okay, at time equals to 0. Okay, this is about the clock. Okay, clock rise from zeros to VDD level. Okay, When the clock rise to VDD level, only then the transistor will start to operate. Okay, the pass transistor start to conduct as soon as the clock signal become active. The directions of the drain currents flow through the transistor will be opposite during the charge up event, logic 1 transfer. Okay, so you see the directions of the currents here. Okay, this is about when the transfer, when the input is 0. Okay, just now okay, never mind. Okay, this one you see that when the input is 0, here the directions of the drain current is opposite. Okay, is opposite. Okay, with VGS equals to VDD and VDS equals to Vmax, the pass transistor operate in linear region. Since VDS is lower than the VGS minus the threshold voltage. Okay, the circuit is analyzed for the this circuit is analyzed for the logic 0 transfer event. Okay, this is the simplified equivalent circuit. Okay, so this is for the transfer 0. This is logic 0 transfer. Okay, and then the graph of this logic 0 transfer. Okay, this is the graph. You see that initially the Vx, okay, Vx at the node of the transistor, okay, is high, okay, is at level. Okay, here already mentioned Vx initially it is Vmax. So the plot here it is start from Vmax, and then when the clock rise to VDD, then the node voltage Vx will drop from Vmax to 0. Okay, in this event, this also shows that the current is flow in the opposite way, and then there is a discharge event. Okay, the charge is discharged from the capacitance. Okay, it is since that the voltage drop from its logic high level of Vmax to 0 volt. Hence, unlike the charge up case, the applied input voltage level, logic 0, can be transferred to the soft node without any modifications during this event. Okay, so that is about the dynamic logic circuit, okay, that show you with the pass transistor, the NMOS. Okay, so now I will explain about voltage bootstrapping. Okay, what is it about voltage bootstrapping? Okay, the examples that are going to show is the inverter. Okay, is the inverter. Sorry, it is not inverter. Okay, so okay, there are two NMOS. Okay, this is an enhancement type inverter. Okay, it is an inverter. Okay, a very useful, okay, a very useful dynamic circuit technique for overcoming threshold voltage drop in digital circuit. Okay, the output voltage may suffer from threshold voltage drop in several circuit structures. Okay, for example, pass transistor gates or enhancement inverter and logic gates, which does not allow voltage swing from 0 to VDD for logic 0 and 1 respectively. Consider the enhancement type circuit in figure 9.11. Okay, this is the enhancement type circuit, okay, with two NMOS, okay, M1 and M2, and the output is connected to the Cout. This is the output capacitance. Okay, so in this circuit, there is a threshold voltage drop. Okay, there is a threshold voltage drop, and then this circuit can use to sorry. Okay, just I repeat. I want to correct what I say just now. Okay, so this circuit, we explain to you how to overcome the drop of the threshold voltage in a dynamic circuit. Okay, this technique is one of the technique. Okay, I will explain here. Okay, using this circuit with the two NMOS. Okay, so you see that when the V in, okay, this is the conditions given for V in is equals to 0 and the Vx is equals to VDD. Okay, so when the input to the M2 is VDD, so the transistor will be on, and when the input voltage is a 0, means it is low, so this transistor will be off. Okay, and the output, okay, this is output, it will be equals to VDD minus VT. Okay, VDD minus VT. This is the threshold voltage drop. Okay, suppose V out must be equals to VDD. Okay, when this transistor turn on. Okay, but this circuit, okay, may also suffer from the threshold voltage drop, means that it is deducted by some threshold voltage of VT. Okay, uh, we need to overcome this threshold voltage drop. Okay, so how to overcome? Okay, there is another modifications on the circuit. Okay, this is the modifications of the circuit. Okay, using the capacitance. Okay, there is additional capacitance that are added at the input of the transistor, and also with another transistor M3. Okay, this transistor M3, it is connected to VDD. Okay, this circuit has a show and also has a study to overcome the threshold voltage drop, and also it can obtain a full logic high level VDD at the output node. Okay, this also means that the voltage Vx must be increased. Okay, the Vx here is at the output. Okay, there are some of the theory here I didn't mention. Okay, how this is being uh, used to solve to overcome the threshold voltage. Okay, I didn't mention all the theory here because I don't think it is necessary. I just want you to learn and know. Okay, this circuit can use uh, to overcome the threshold voltage drop. Okay, so this one since there is two additional capacitance here, Vs and C both. Okay, Cs is the parallel combinationals of the uh, source to substrate. Okay, capacitance. Okay, this is source to substrate capacitance. Okay, the capacitance is not sure in here in this circuit. Okay, but there is a capacitance. Okay, it can be junction capacitance. Okay, later on I will further mentions on the parasitic capacitance and then the load capacitance. What is all this? Okay, after the dynamic logic circuit, I will further mention on capacitance and resistance. Okay, and as well as the interconnect, all this. Okay, so for this one, this is another capacitance that is uh, for this transistor. Okay, so and then there is also a capacitance is get to the substrate. Okay, capacitance. So it illustrate what is CS. Okay, and then C booth is the capacitance in between Vx and Vout. Okay, means that C booth here, it is between this Cx node and then this Vout node. Okay, so these two are in parallel. Okay, maybe I should not say it's in parallel. Okay, it can be in parallel because if can connect like this. Okay, but in this case, maybe I don't mention them in parallel because they may not be in parallel. This doesn't look like in parallel. Okay, so under the conditions where the C booth is larger than the CS, okay, then we will get this output. Okay, when the input, okay, this input is the input to the transistor M1. Okay, when it is logic 1, that means that the M1 is turned on and the output here becomes 0. So this we can understand. And then for case 2 is when the input voltage is logic 0. Okay, when it is logic 0, that means it is off. Okay, when it is off, V out then must be equals to VDD. Okay, so when C booth is larger than CS, then C out will be VDD. If C booth is less than the CS, the V out will be equals to VDD minus VTN. Okay, this is the difference. Okay, for this circuit. Okay, so there are also some of the formula here. Okay, I include in the slide. Okay, later I will upload to you. Okay, for your lecture notes. Okay, so this one also I will not further explain. Okay, I show only. Okay, also at the same time, I let you to further study. Okay, if you want to know what is the relationship between the C booth and the CS. Okay. Okay, so the equations here uh, given here is actually about how to get the C booth and how to get the Vx value. Okay, the Vx value through the values of C booth and CS. Okay, and then the formula that I want to emphasize here, okay, is this formula 9.29. Okay, this formula. Okay, this is differentials of Vx over dt equals to C booth divide by CS plus C booth multiply the differentials values of V out over Vt. Okay, these equations shows that the increase of the output voltage V out during this switching event will generate a proportional increase in the voltage level Vx. Okay, so this is the relationship between Vx and V out Okay. Okay, and then also there is another formula Vx. Okay, when we evaluate it as Vmax. Okay, sorry, when we evaluate the Vx when the C booth larger than Vx. So this is the formula. Okay, and if we want to determine the Vx mean, we can use this formula. Okay, okay, this is just for your information. Okay, I think I stop here. Okay, uh, the next few slide is not ready. Okay, not all is ready for you to know. Okay, so I will not be covered today. Okay, so now let me see. Okay, I still got a lot of time. Okay, anyhow, I still need to end the class early today. Okay, so I think that is a good news to you. Okay, so I guess all of you don't have any question, right? Okay, so I will leave it to you to study later. Okay, hopefully you you do the revisions before you take the exam. Okay, okay, let me see the attendance. Only three. Okay, okay, so I see that the number is correct. I received all the attendance form. Okay. Okay, no further issue. Then we can dismiss class now. Thank you. I will see you on Monday, next Monday.